Hello everyone. Welcome back to my channel. Today, we will be exploring a crucial topic in electrical and communication transmission lines, the skin effect. If you are visiting my YouTube channel for the first time, don't forget to support the channel by liking this video and subscribing to the channel. Hit the notification bell so you never miss an important tutorial like this next time. Have you ever been curious about how electricity moves through AC transmission lines? What actually occurs in these lines when current flows? Does the current remain inside the conductor, or does it migrate to the surface? If it does move to the surface, what causes this phenomenon? Is it beneficial or detrimental to the system? Stay tuned, because by the end of this video, you will have clear understanding to all these questions. Let's begin. When you hear the term skin effect, what comes to mind? Skin effect refers to the tendency of an AC current to distribute unevenly across the conductor's cross-section, with the current density concentrating on the outer surface of the conductor. This causes gradually decrease of current toward the core of the conductor. Consequently, the core of the conductor carries less current compared to the outer regions, which leads to an increased effective resistance of the conductor. It is essential to note that skin effect does not occur in direct current systems, as the current in such systems remains uniformly distributed throughout the conductor. However, in alternating current (AC) systems, particularly those operating at high frequencies, such as in radio communication and microwave transmission, the skin effect significantly influences the design and performance of transmission lines and related components. Now, let's delve into the causes of skin effect in transmission lines. The skin effect arises due to the interaction between the magnetic field generated by the AC current and the conductor. As AC current passes through a cylindrical conductor, it creates both an external and internal magnetic field. The frequency and amplitude of the AC current determine the behavior of this magnetic field. According to Faraday's law of electromagnetic induction, a fluctuating magnetic field induces an electric field within the conductor. This induced electric field, in turn, generates opposing currents, known as eddy currents, inside the conductor. These eddy currents resist the original AC current. Eddy currents are more concentrated toward the inner of the conductor, where the magnetic flux linkage with the AC current is stronger. Conversely, near the conductor's surface, the linkage of magnetic flux is weaker due to the higher magnetic reluctance of air. As a result of this, stronger opposing electric fields develop within the inner, reducing the net current density. Meanwhile, at the conductor's surface, where there is minimal magnetic flux linkage, the eddy currents are weaker, and the opposing electric field is lower. This leads to a higher net current density at the conductor surface. This unequal distribution of current, where more current flows near the surface rather than the core, defines the skin effect in transmission lines. It is important to note that the skin effect is negligible at low frequencies less than 50 Hz, and conductors with small diameters less than 1 cm. Now, how can we measure the degree of the skin effect in transmission lines? The skin effect is quantified using the term skin depth, which is the depth below a conductor's surface where the current density decreases to approximately 37% of its surface value. A lower skin depth signifies a higher skin effect. In transmission line designing, achieving a high skin depth is preferable for optimal performance. Now, let's examine the key factors that influence skin depth when designing transmission lines. 1. Frequency of the AC current. Higher frequencies result in more rapid changes in the magnetic field and stronger eddy currents. Consequently, Skin depth decreases as frequency increases. 2. Conductor's conductivity. A higher conductivity reduces resistance, making it easier for eddy currents to form. Therefore, as conductivity increases, skin depth decreases. 3. Conductor's permeability. The higher permeability leads to stronger magnetic flux linkage and more intense eddy currents. As permeability increases, skin depth decreases. 4. Conductor shape. Different shapes affect magnetic field distribution and eddy current behavior, resulting in variations in skin depth across different conductor geometries. But friends, why should we be concerned about the skin effect, and how can we mitigate it in transmission lines? The skin effect presents several challenges, including: first, increased power losses and conductor heating, which decrease system efficiency and reliability. Lastly, higher impedance and voltage drops in transmission lines, affecting signal quality and power delivery. Now, what are methods to reduce this skin effect? Engineers employ several strategies. 1. Selecting conductors with high conductivity and low permeability, such as copper or silver. 2. Using conductors with smaller diameters, or cross-sectional areas. This promotes more uniform current distribution across the conductor. 3. Employing stranded, or braided conductors instead of solid conductors. This increases the effective surface area and reduces eddy currents. This minimizes the skin effect by ensuring each strand occupies different positions over its length, maximizing surface area for current flow. 4. Utilizing hollow, or tubular conductors instead of solid ones. This reduces weight and cost without significantly impacting performance. Since the inner core carries minimal current due to the skin effect, it can be removed without major drawbacks. Lastly, reducing the AC current frequency, which increases skin depth and mitigates the skin effect. However, this approach is not always feasible for applications requiring high-frequency signals. In conclusion, the key point of every engineering designs and constructions is to reduce losses and cost. When designing AC power transmission systems, it is crucial to consider the skin effect. This phenomenon significantly impacts power systems and conductor performance, necessitating careful management in system design and operation. That brings us to the end of this session. If you found this tutorial helpful, don't forget to hit the like button, subscribe, and ring the bell for more insightful content. Feel free to share your questions and thoughts in the comments section below. Thank you for watching, and I'll see you in the next video. Stay safe. Goodbye.